Good evening all, and it's really nice to be here. Thanks to Ibnor and Hafiz for inviting me. And it's great to see so many of you interested in ocean exploration. It's one of my passions. It actually started with taking inspiration from nature. While I was doing my undergrad, I started looking at insect flight, and that's when I got interested in natural phenomena. And I was very fortunate to find this research lab with MIT Alliance, who work on bioinspiration but for ocean exploration. And that's where it all started. So I'll just start off with a little video. You might have seen this going around online. So it's really deep. There's a whole new world out there, and this was actually my experience when I went for scuba diving for the first time. When I just dipped my head, it was like a whole world out there, and it's interesting that after all these years of technological advancement, only 5% has been explored. So I'll start off with traditional vehicles which are currently used for exploration. There are many kinds of vehicles like surface vehicles, underwater vehicles, ROVs, submarines, even divers going down to explore. But there are problems with each of these systems. The next slide would show one of them, which is a huge problem. It's called biofouling. Whenever you put rigid parts, rigid vehicles underwater, things start growing on them, which is not good for the vehicle, which is not good for the ocean as well. And this happens when the vehicles are there for long-term exploration or long-term missions. And you can see a diver going down to clean ship's vessel, and this is how it's been happening so far. They send down divers, or they just started to make ROVs which can clean biofouling, but it's not very advanced yet. The other one is it's also intrusive. There's actually a picture of a shark thinking an AUV is a food and tries to eat it, and it gets harmed. Below are pictures of animals getting hit by propellers, and there are many cases of this, and some of them are even humpback whales, which are threatened species. So these kind of vehicles, these kind of exploration technologies are intrusive. They affect the marine environment. Moving on. Also, some of the sensing methods that has been used currently, they are also harmful to the marine animals. For example, sonars really disturb the whales and the ocean and the dolphins. and they start moving out of the deep sea to the shallow waters, and they are disoriented and they die because they're completely disoriented. They don't know where they are and they cannot locate each other. And this is also another big problem with traditional methods of sensing. So starting off with this is one of the major motivation to look into nature itself for inspiration for building technologies. I strongly believe that you just have to look into nature and you can find solutions for whatever problems that you want, because nature has evolved. I mean, the evolution has gone on for millions of years, and it has perfected a lot of things that we actually need. So I start off with one example. This is a blue spotted stingray. So you can see how gracefully it moves underwater. I think it was filmed somewhere in Phuket. So very graceful, very smooth, and the motions are like organic. So these kind of animals, stingrays, manta rays, they are in the class of animals called batoids, which use this wavy motion on their fin to move around in the ocean. And that's how they are able to be very, very maneuverable. A stingray can make point turns if it wants, or if it can bank, and it can do all kinds of maneuvers that you can think of. So we looked at a stingray and we took inspiration to make a stingray robot so that it can be highly maneuverable. And another idea was also to make it very simple, without many mechanical components. The whole body, we wanted to encapsulate it in silicone, which is sort of eco-friendly. Things will not grow on this. It's an anti-biofouling material. So we took an example of a stingray. We study how it behaves underwater. We study the interaction with the fluid, and then we made this stingray robot, which can mimic the motion of the fins. And that's how there's a video of the robot doing some. Okay, there's another field deployable version that we did. We tested it in a few swimming pools and even a little bit of sea trials. There's a video showing how the robot maneuvers. So it exactly mimics stingray motion, and it's able to be very maneuverable. The idea is, if you also put these robots for exploration in the ocean, it's not going to interfere with the marine environment. They can blend in with the environment and still get your measurements, whatever you want to explore, water quality measurements or images or anything that you want. And another advantage of stingray design is that it has this huge fin, which is almost the size of its body. Which means you can put a lot of payload. The field deployable version that we developed, we could actually put 3 to 4 kilograms of payload, which means all that is sensors apart from the robot mechanism itself. So it can actually be used as a field deployable robot, which you can use in oceans or reservoirs or wherever. We can move on. The second example I want to show is the class of animals called cephalopods, which is basically octopus and squids, and I think I gave it away, but yeah. So octopus are one of the most intelligent animals. They camouflage really well, and we still don't know how they do it. But one other thing they do is they have this mode of propulsion called jet propulsion, where they basically change their shape rapidly in order to jet forward. That's what happened right now. It got threatened by the person who was filming, and then it jetted a blue ink, and then it moved forward really fast. And these are one of the fastest invertebrates underwater. So this almost moved like 10 times its own body length in less than a second. So we thought that this could be really useful if we want to build systems. This could be a nice way of propulsion. So we started looking into effects of changing shape underwater and how that improves performance. So I built a little model that emulates an octopus shape change. And this particular model, we did a lot of tests in the lab, and we found that it can actually achieve the what an octopus does. It goes like 10 body lengths per second, and this happens because of change. So it starts off as almost like a ball, but then it shrinks really fast into a streamlined shape. It's almost like a bullet, and the octopus is really smart that it has figured this out. So it's kind of counterintuitive. If you want to move something huge in underwater, it's difficult. There is a lot of drag, but then when you shrink into a streamlined shape, you kind of get energy back from the surrounding fluid, which propels it much faster than a normal vehicle with a jet. So so we just mimicked this and we made this model, and it proves to be really efficient and performs really well. It's a slow motion video of the robot. I mean, if you're interested in the graphs, there is below. So the efficiency goes more than 50%, 60% with this mode of propulsion, and we can go up to 10 body lengths per second. For just for a comparison, 10 body lengths per second is almost like driving a Porsche underwater. It's like 0 to 97 kilometers in like 2.5 seconds or something. So this mode of propulsion can be either put in existing vehicles, or you can make vehicles which use this kind of shape change to achieve very fast maneuvers, very fast motions. And by this you can cover large areas very quickly. You can take measurements very fast. And again, because it's biomimetic, it's not going to interfere with any of the marine life. It's going to be fast and efficient and eco-friendly. The next one is an example of a turtle. Turtles are also highly maneuverable, and little is known about them. They are actually they have a lot of endurance. They can travel like hundreds of kilometers, thousands of kilometers without a problem. And they use this particular mode of flapping, which is very unique in nature itself. It's 3 degrees of freedom motion of its fins, and this is actually a very efficient way of propulsion. We did some tests on this kind of 3 degrees of freedom motion, and we found that you can generate a large amounts of thrusts just by mimicking the way it moves. So it flaps, it rotates, and then it also does a sweeping motion. So when it moves forward, it sort of does like an eight figure motion, and that's how it's able to maneuver. And these are also very highly maneuverable. They can make point turns. They can flip back and stuff. So yeah. So we took inspiration from this, and then now I'm developing a turtle robot. So the idea is to have this kind of flapping propulsion as the primary propulsion system, and we can really use it for as underwater vehicles with to deploy structures, to maintain structures. For the example that I showed, where they send divers down to clean stuff, we can use robots to do it. We don't need to send divers, because these robots can generate large amounts of forces, and you can really have like arms manipulators in it, which can do all the functions that that is required. So and the idea is also to keep these robots simple. Like I said, we don't have a lot of mechanical links in the robot. We keep it we try to keep it as like a soft robot, or a shape inspired from nature, so that we can have many robots collaborating to do a mission. These are large structures called recons and oil booms, where they fill these with oil and they drag it along the ocean. But right now it's done by tugboats. They have people throwing this out to deploy. So we can really have, like, imagine 10 or 15 of the robots doing this, and they just come back to the ship. So it's a much more efficient and a nice way to do things. The other example, we'll go to sensing.
If it wanders out of the dark part of the cave, other fish can see it, but it won't see them. The blind cavefish needs to stay in the dark where it's safe. My lights make the cavefish swim for cover and safety. The fish that follow me into the cave from outside take an interest in the cavefish. I have to shoo them away. In fact, in the cave ecosystem, this little fish is the top predator, the great...
So this is a clip from one of the documentaries on this blind cave fish. So these are found in Mexican waters, and by evolution they are blind because they live so deep underwater where light does not reach. So they didn't find any purpose to the eyes. The eyes got covered, so they don't have eyes. But how they move around is they around the body. They have this very complex sensory system called the lateral line. These are so it's all around from the head to tail. There are micro sensors embedded in the body, and these sensors detect very tiny flow variations. And by sensing these flow signatures, they can know what is around them, and that's how they navigate around they navigate around dark caves, and they are very fast also. They are one of the best predators in the caves. And they're able to do this by these microsensors. So we took inspiration from these sensors, and we thought, I mean, if this is used in vehicles or wherever you need flow sensing, this is something very useful. So we developed a microsensor. You can see a small picture at the bottom right. And the next page, I think, will show a comparison with a 10-cent coin. So that's one sensor on a Singapore 10-cent coin. So these are really micro sensors, but they detect flow variations, both velocity and frequencies. And you can really embed like arrays of these sensors wherever you need to measure flow. And the principle works the same in water and air as well. You can even measure airflow with these sensors. So yeah, and I think there's one more. Yeah, so this is a final inspiration. So we looked at seals, and how seals move around is they use these whiskers on their face, and they do not use their eyes or their ears. They only use their whiskers, which are also very effective flow sensors. They can detect flow velocities and frequencies. They did some tests on a real seal. So this picture here, the blue line is actually they let a fish go around in the water, and then they blindfolded a seal and let it in the water, and then it exactly followed the trace of the fish even after 30 seconds after the fish has passed. And they figured that it uses the whiskers completely to do this. So these are also very effective flow sensors, and it will come in handy wherever we need to measure flow signatures. So we took inspiration and we made a sensor out of this. There's one video, and we found that it's also the seal is also very smart. By evolution, they've developed this very intricate structure on their whiskers. So the whisker structure is something like this. It has undulations, and it's an elliptical cross section. And with this, it's able to reduce the vibrations that it might experience. So normally, when even if you drag your hand underwater, or if you have dragged a cylinder, you would have seen that it vibrates a lot. This is by physics. Whenever you drag some object underwater, there is vortices induced, and the vortex causes vibrations. It's called vortex-induced vibrations. But this particular structure of the whisker completely eliminates vortex-induced vibrations, and therefore they act as super efficient sensors. We found this, and then we developed whisker sensors. We made these sensors, which we then deployed on traditional kayaks, autonomous kayaks, and then we took it out to the ocean, and we tested them, and they work really well in detecting flow variations. And so these act as both the micro sensors and these kind of whisker sensors, they act as near field sensors. Sonars usually beam for very large distances, but these are near field sensors where you can get information right next to the vehicle, which is sometimes important in waters like Singapore waters, which is very cluttered. Or if you are going to deep caves, you need information right next to the vehicle sometimes to maneuver really well. So these whiskers can be used as flow sensors on marine vehicles. And we also do look at traditional vehicles. We don't disregard them, but we use it as a platform to test autonomy. So we take it out to the sea every 6 months. We take these robots out from Tuvas. We go down, or from the northeast we sail out, and we test these robots to see how they collaborate and perform missions. And once the autonomy is fully developed, we would implement it on the Biomimetic robots. So we can send those robots out performing collaborative missions. So these are currently our testbed platforms, which we will later put it on the bio-inspired robots. So yeah, the idea is to have many of these robots exploring the oceans in a very eco-friendly way, and to go where no one has gone before, but with robots. Yeah.
Thank you so much, Vignesh, for the very entertaining talk.